equation and its applications. So there are many Doppler equations. It's not just one, as you will see, but
basically it centers on how we calculate flow, the applications of flow calculation, and then pressure gradients and examples of where we use pressure gradients. So we'll start with some terms that we need to define using fluid mechanics. We often use the term pressure. What is the definition of pressure? It is force per unit area. And so if you use the SI system for measurements, it's dynes per centimeter squared or Newton per meter squared. 1 Newton per meter squared is 1 Pascal. Since pressure is given by force divided by area, I can remove force and use Newton's second law, and then I have mass multiplied by acceleration divided by area. We all know that mass is the product of density and volume, and because we are talking fluids, we are more interested in volume as opposed to mass, and that's why we do this change. If you say volume divided by area, you end up with a dimension. And so the pressure can be given as the product of density of that particular fluid, the free fall acceleration, and the distance is the height above the center of gravity. So for water, if we use 1 centimeter of water, and you go through the calculation and you say the acceleration is 9.8 meter per second squared, and you convert that to centimeter per second squared to express it in dynes, because this is a small height and a small pressure head, if you would. That translates to 1 centimeter of water exerting 980 dynes per centimeter squared. We often use the term, the pressures in millimeters of mercury, and since mercury has a higher density than water, as you expect for the same height, the pressure will be higher in terms of millimeters mercury. And so that is the pressure that is exerted. How about I want to convert pressure from centimeters of water to millimeters mercury? If you divide these, you will end up with 1 centimeter of water exerting about 0.74 millimeters mercury pressure. Okay. So that's pressure. How about flow? If you think of flow in a blood vessel, and you say blood vessel is like a cylinder, so then I'm interested in the volume of that cylinder, and I want to know the flow through the cylinder. We assume that the cross-section of the cylinder is a circle. It can also be assumed to be an ellipse, and we'll show you that. So for veins, it's more ellipse or ellipsoid. For arteries, it's more spherical. Flow is given by area multiplied by velocity. If you look at these units and you multiply them, you will see it is volume per unit time. If it is a cross-section of a circle, then this is 3.14 multiplied by the square of the radius. Of course, multiplied by velocity if I want flow. If it is an ellipse, then I need to get the two perpendicular, we can call them diameters. There will be a longer one and there will be a shorter one, and this is where that comes. Let us talk now about flow in a tube. Why is it important to know flow in a tube? As you will see, there are some principles that apply to flow in blood vessels that are of interest to us. So if we think of no impediment to the flow into the tube, as the fluid progresses along that tube, the layers of the fluid that come in contact with the wall of the tube will have zero velocity, and then that velocity keeps getting higher and higher as you move towards the center where the velocity is highest. So it has the shape of a parabola as you see here. The distance from when the fluid enters to when this shape is well formed or developed is referred to as the entrance length. What is the resistance to flow? So we are familiar for solid objects, we talk friction. For fluids, we talk viscosity. A liquid that has higher viscosity will face higher frictional forces. Blood behaves as a Newtonian fluid. What does that mean? It means that the shear tension and the velocity gradient are related to one another. So if I want to express that relation and then show you where viscosity comes, this is the shear tension and this is the velocity gradient. It is a velocity gradient in terms of space, distance, not over time. Velocity over time, as you know, is acceleration. So this is the relation that we are interested in. They are directly related to one another, and if we remove that proportional sign, we have in its place the viscosity. We are interested in viscosity, so we rearrange that expression, and if you take a look at it, this is the shear tension, and now we have the distance in the numerator and the velocity in the denominator. That will give you the units of Pascal second. This is Pascal, and this translates to second. So that's the unit of viscosity. Now let us take a look at what are the factors that affect flow in pure physical terms, if you would. And then we will see how we modify these terms to be applicable to flow in a blood vessel. So we say flow goes from point 1 to point 2. For flow to continue or to occur in the first place from point 1 to point 2, there has to be a pressure difference, where pressure in point 1 is higher than pressure in point 2. We will assume that the length of this distance is given by L between points 1 and 2, and we will also assume that the cross-section is a circle for ease of the calculations. So as we just said, the velocity is 0 at the place where the fluid meets the wall of the tube. The velocity is highest in the center of the tube, and as you go between the center and the wall of the tube, the velocity will keep decreasing till it reaches 0. The radius will be given by A for the actual tube, but then I can also take smaller and smaller cylinders of fluid where the radius for these corresponding circular cross-sections is given by R. At equilibrium, the force that is letting blood move from point 1 to point 2, which we can describe it with the term pressure force, will be balanced by the friction force, the one that wants to stop the flow. So pressure, as if we are interested in converting this to force, I multiply pressure by area. And for the viscous frictional forces, it is given by the shear tension that we see here, multiplied by the surface that it is exposed to. The surface here is the surface area of a cylinder. And that's why it is 2 pi r multiplied by L. I won't take you through the math, but it involves some integration to end up with that maximum velocity given by the difference in pressure. So the higher the pressure, the higher the velocity, and it is inversely related to the length and inversely related to the viscosity. These are the factors that want to slow blood, and directly related to the square of the radius. We are interested in flow. So therefore, one would take the next step and say flow is given by area multiplied by the mean velocity. And it can be shown by simple calculations that the mean velocity is 1/2 the maximum velocity. So now we go into that term and we remove the maximum velocity and put in its place the mean velocity as a squared over 2. We rearrange this expression, and if we say flow, now flow is directly related to the 4th power of the radius, to the pressure gradient, inversely related to the length and the viscosity. If you want to talk in terms of resistance, then resistance is directly related to the length and viscosity, and inversely related to the 4th power of the radius. So of the variables that you see, the one that can carry the largest effect on flow or resistance if you change it, or if it gets changed as you move, say, from larger to smaller vessels, it's that radius. Let us, that was Poiseuille's law, then let us modify that to flow in blood vessels and see what of these principles still holds. We've assumed in the calculation that the viscosity is constant. It is not changing as we go from outside to inside or from larger vessels to smaller vessels. In general, this is a valid assumption till you reach vessels really small in size, less than 0.5 to 1 millimeters, which we do not examine by Doppler. Why does it change? Because now the proportion of red blood cells and plasma is changing into these vessels. We assume that the flow is laminar, and in a normal circulation, this is the case, except for a short, very short distance as blood emanates from the valves and is flowing in the root of the PA and the aorta. We said it is a circular tube cross-section, but in many situations, these vessels can be tapering. We make the assumption that as blood flows, the diameter or the radius does not change. The truth is these are vessels that are elastic and will expand. This carries the largest effect in terms of errors of at least 10%. Steady flow is the assumption that we went through, but as you all know, it is pulsatile. Here you can look at the temporal profile of flow, and you can use temporal averages. Another item we pay attention to is the likelihood of turbulence. Many times we describe turbulent flow. For turbulence to happen, the inertial forces have to exceed the viscous forces. The inertial forces are the ones that want the fluid to move, keep moving. The viscous forces are the ones that want to stop it. Inertial forces are directly related to density, velocity, and diameter, and viscosity is the main factor for the viscous forces. You can go through the math here, and you replace density by mass over volume, and then you look at these terms, and you end up with force multiplied by velocity multiplied by diameter, divided by acceleration multiplied by volume, because mass is force divided by acceleration from Newton's second law. Long story short, you will see that the numerator has the units of Pascal second, and the denominator also has that unit. So the Reynolds number is dimensionless. It has no units. We already covered the flow. So now we said that to calculate flow, I need to calculate area and I need to calculate velocity. There can be errors in the calculation of the area that translate to errors in the calculation of flow. If I measure the diameter incorrectly, then yes, there will be an error in the area. If I make the assumption that it is circular cross-section and it is not, then I've used the wrong expression to get that area. We've made the assumption that that flow or that area doesn't change throughout the duration of flow, say during systole, but then there are instantaneous changes in the area. A clear example is in the PA, and there can also be seen in aortic valve stenosis. Absolute flow and changes in area. If you force more flow through a narrow orifice, that area can increase. That is made use of, as you know, with dobutamine stress echo to look at low flow, low gradient aortic stenosis cases with depressed EF. The appropriate site of measurement for diameter. For flow to be accurate, I have to measure the diameter and thus the area and the velocity at the same level. If they are not measured at the same level, then there can be problems because the area could be different at the site where the velocity is measured. And to circumvent these assumptions with diameter and converting them to area, there were efforts earlier on, not necessarily very active now, of replacing diameter by area. And here, if I planimeter the area incorrectly, then of course that also will lead to error. A frequent question is, if I make an error in the diameter measurement, what error does that change in terms of area calculation? Many think I'm squaring it. This will be what you see. This is a simple algebra expression that shows you that the error in the area measurement is really twice the error in the diameter or dimension measurement. So important to keep that in mind. So we covered errors in area measurement. How about errors in the velocity measurement? So the first assumption that we make is across that cross-section of flow, the velocity is the same. Sometimes it's close. This is true. Sometimes it is not. The velocity profile that you record with pulse wave Doppler, for example, has red blood cells moving with different velocity. And so if I use the incorrect component of that spectral profile to get the velocity, then there will be errors. We will see real examples of that shortly. It would be best to get the 3D representation of the velocity vector, and at times it is challenging to do that. That's why we want to always align with the flow as much as possible with minimum angulation. The larger the angle with the direction of the flow, the greater the error here. Signal strength. If the signal that I get of the velocity or of the flow by pulse wave Doppler is weak, then I can trace it incorrectly, and that will lead to error. Example of that, when you have someone on mechanical ventilation, sometimes when the vent is on during inspiration, you see weaker amplitude signals. What do we do in that situation? We record more cycles, so now we show you the flow when the vent is not pushing air in. We talked about have to measure diameter and velocity at the same level, but they are not, in terms of time, they are not really measured simultaneously. For example, flow through the LVOT, I measure the diameter in the parasternal long axis view, then I go to the apical view and get the velocity. What happens if the cycle length is different? Examples of cycle length difference could be patients with atrial fibrillation, particularly uncontrolled and faster rates, could be patients with frequent ectopic beats. What is the solution to this situation where you see a lot of beat-to-beat variation? Ideally, you want to average, and also ideally you do not want to record flows where the cycle length is so short that the valve does not actually open and there is no flow into the systemic circulation. And then the last assumption is assumption of continuity. What does that mean? It means that if I measure flow in the LVOT, this is, say, the same as flow in the ascending aorta. May be correct, may be incorrect. Remember that between the LVOT flow and the flow in the aorta, above the level of the valve, there is flow into the coronaries, so the flow will be less by the amount that leaves the coronaries and so on. Since we can calculate flow, we can calculate stroke volume and cardiac output. So the stroke volume is given by the product of the cross-sectional area and time velocity integral. So here the flow will have the units of volume. As you see these expressions, area is centimeters squared, and the time velocity integral, which is the product of time and velocity, will have the units of a distance. And I can have another expression if I want to do the 3.14. I can do 0.785 by the diameter squared times TVI. Either of these will get you the same result. Nowadays, we can trace the time velocity integral directly, and by calculus, you get a very accurate value. You can also say, I'm going to make my life easier. I'll say it looks like a triangle, and then the area of the triangle is half base times height. In any event, once I've calculated stroke volume, I multiply it by heart rate. This will give me the cardiac output. If you have good alignment with flow, if you have reasonable measurements of area, these measurements of cardiac output are usually solid and reliable. The measurement of cardiac output has had numerous applications. Drug therapy, for example, you take someone with low cardiac output, you give them a positive inotrope, and you see what happens to the stroke volume. Different pacing modes, different AV delays, and you see how that affects stroke volume and, in turn, cardiac output. Look at physiologic changes that happen, for example, with pregnancy and delivery, in fetuses and neonates, and certainly with exercise. Why do we care for flow calculations? We care for flow calculations because we can calculate shunts, we can calculate regurgitant volume, We can calculate valve area. We also can have an estimate of ejection fraction. If I have a reasonable assessment of the size of the end diastolic volume by, say, 2D echo or 3D, and I have a stroke volume by Doppler, and there is no significant regurgitation, then that could be a value to have a feel for what the ejection fraction should be. So let's look at examples of measuring flows. The first one is in flow in the LV outflow tract. We go to the parasternal lung axis view. We want to zoom. Why do I want to zoom? To make my errors less costly. And then we get the diameter when the aortic valve leaflets are open. We go to the apical view. We record LVOT flow by placing pulse wave Doppler sample volume just below the level of the aortic valve. You can see one click of the valve closure, but you should not see both clicks. If you see both clicks, then you are inside the valve. We do not want to record flow in the valve. We want to record flow in the LVOT. The second point I want to bring up, you see the brightness here, that bright green color. You can see fainter color here. The brightness is directly related to the number of red blood cells causing that reflection. The more the red cells, the brighter the signal. And so we go after what we call that modal velocity when we trace the time velocity integral. We can record flow also in the RV outflow tract and in the pulmonary artery. This is a lung axis view that shows you the PA, and you see the pulmonic valves. Sometimes it's challenging to get a good measurement of the RVOT and of the region below the pulmonic valve, something that can enhance this acquisition. This is more of a challenge in adults, less of a challenge in children and in individuals with a thin chest wall. You can put color so as to sort of show you where the flow is from one edge to the other wall. So now I measure the diameter and I do the time velocity integral. Again, one click, not both clicks, and I can combine them with the expression we just saw, and now I have flow through the RVOT. For the mitral valve, we get the mitral annulus diameter, and we combine that with flow at the level of the annulus. Because the mitral valve is closer to an ellipse in cross-section than to a circle, the ideal is to get the mitral valve diameters from both apical 4 and apical 2 chamber views, and then use the ellipse equation. Having said that, there are some validation studies that said we will assume it's a circular cross-section. We will just do the apical 4 chamber view diameter, and let's see flow here against a PA catheter. And it turns out to be does not affect the accuracy that much if you do a circular assumption. The other point to bring up about recording mitral inflows, we typically record the inflow at the level of the annulus and also at the tips. You do not rely on mitral inflow at the level of the tips to quantify flow. You rely at the level of the annulus. Why do I still want to record flow at the tips? This is the level at which we do measurements as E to A ratio deceleration time, which would be needed for diastolic function assessment. Now let us see how we use the flow examples we talked about, the principles we talked about to quantify a mitral regurgitation case. So basically, when the ventricle contracts from end diastole to end systole, it will send blood in two directions, one through the aortic valve, and one will go back into the left atrium through the mitral valve. We want to know this volume. And so we say the stroke volume is the sum of both the aortic flow and the mitral regurg. And therefore, the mitral regurg is the difference between the stroke volume, difference between end diastolic and end systolic volumes by 2D, for example, and aortic flow. Also, we can say that stroke volume is given by flow across the mitral valve during diastole. So let us see an example here. It's sort of stuck, doesn't advance. Can you help me advance? Okay. So this is a patient with a flail segment in the posterior leaflet, and this is an apical view showing you where the Poiseuille is forming. It's an incomplete Poiseuille. Wouldn't be a good one to quantify flow by that method, but the utility of that view and the information we get out of it is we see a large jet that is heading medially. Typically, these jets will head anteriorly and medially. What if we want to quantify the flow here? So we go to the mitral annulus diameter. We get the mitral inflow across the mitral annulus by pulse wave Doppler. We get the LVOT diameter. We get the flow across the LVOT diameter. I'm not showing you the scale, but each of these is 20. If you just a quick look, you would say this looks small, right? And indeed it is small. Why is it small when this is a normal contracting ventricle that is even enlarged? Because a lot of blood is going in the wrong direction. So even if you do not want to quantify, paying attention to that time velocity integral is useful. So now we have that diameter, which is quite big. Many of these patients develop mitral annular dilatation. There is the time velocity integral, and there are the corresponding values. So now we say the mitral valve stroke volume. This is the volume that will fill the ventricle during diastole from the mitral valve, is given by 113 milliliters. How about the blood that leaves the ventricle and goes through the aortic valve to the rest of the circulation? That is 42 milliliters. So the regurgitant volume is pretty large. This falls into the severe category without you knowing what the sort of cutoffs are. You can appreciate that it's a huge difference. We can do the same for the aortic regurg. There is bicolor Doppler, and sometimes you get eccentric jets. Their appearance can be deceiving as to the severity. But if we go through the calculations and we get flow through the LVOT, it's 82 milliliters. Not all that blood will go to the systemic circulation. Some of it will leak back into the ventricle, and the blood that makes it to the systemic circulation I can measure in the RVOT. In this case, it's 54, and so we end up with a regurgitant volume and a regurgitant fraction that falls in the moderate category. So enough of flow. Let us talk now about pressure gradients and how we use that. To introduce you to how we end up with the famous Bernoulli expression, I will take you through the relations between energy, work, and flow. Energy in pure physical terms is defined as the capacity to do work. For solid objects, it's the product of force and distance. For fluids, we remove force and we put pressure multiplied by area, as we defined pressure and force on the first slide. And then if I say area times distance, then that's volume. So then work is given by pressure multiplied by volume. This is one expression. So if you have a pressure volume loop of the right ventricle or a pressure volume loop of the left ventricle, whether by invasive or or non-invasive means with their assumptions, then you can calculate the work that that chamber is doing. Not all the work, but some of the work. If we want to look at other expression for work, so to get this type of work, I need to know pressure and volume. But let's see another example. We can say the work is given by also mass multiplied by acceleration multiplied by distance. This is the force times distance. Force is mass times acceleration. And acceleration is velocity over time, and distance is velocity multiplied by time, which means this expression reduces to mass multiplied by the velocity squared. Remember, in fluids, we do not deal with mass, we deal with volumes. And so here we can say that density multiplied by volumes by the velocity squared over 2. This is the kinetic expression for work. So here, for me to do that calculation, I need to know the volume of blood and the velocity with which that blood is moving. The last expression we can use to derive work is we go back to, again, that mass times acceleration times distance. We leave the mass as is for now. We use the free fall acceleration and the height above the center of gravity. Then I remove mass and put in its place density times volume, and now I have an expression for potential energy. The variable here is the height. The variable for the kinetic expression of work is the velocity to pay attention to, and for the first one, it's the pressure. Bernoulli's law essentially is conservation of energy. For now, we will take a look at flow at 2 points, point 1 and point 2. The main difference between them is the cross-section is larger at point 1 and is smaller at point 2. Flow, however, is the same. That we will assume these are arteries, larger artery, smaller artery, or flow in the LVOT and flow through the aortic valve for now. Flow is equal at both points. And then we said flow is given by the product of area and velocity. And so this product at point 1 equals that product at point 2. And it follows if the area at point 2 is small, this is the continuity equation that we rely on to calculate aortic valve area, for example. But going back in terms of energy and work that we are interested in, if we look at point 2 where the area is smaller, to keep these right side and left side equal, it follows that the velocity at point 2 has to be higher than the velocity at point 1. And so if I am just looking at the kinetic energy portion or part of the work equation, then kinetic energy at point 2 is more than kinetic energy at point 1. What if we go to all components here of energy? So remember we said there is pressure and volume product, there is the kinetic energy expression, there is the potential energy expression. We want to talk about energy per unit volume, so I divide by volume, and now we end up with this. Given the conservation of energy, energy at point 1 equals energy at point 2, and now we have that expression. Since the height above the center of gravity is the same, the potential energy term can be canceled from both sides. And so we have pressure at point 1 plus kinetic energy at point 1 equals pressure at point 2 plus kinetic energy at point 2. I am most interested in the pressure gradient, so I rearrange that expression. And we have the pressure gradient is given by half multiplied by density. This would be the density of blood, V2 squared minus V1 squared. When V2 is much higher than V1, the square of V2 will even be higher than the square of V1, to the extent that if you ignore V1 altogether, make it 0, you do not deviate much from the true value. And so that's the expression that we rely on in the modified Bernoulli equation to get pressure gradients. This shows you how we end up with the pressure gradient given by 4V squared. It's basically a lot of unit conversions. For the sake of time, I will skip that, but it is not challenging to see the approximation here. While we use the modified Bernoulli equation a lot, it has its limitations. What are these limitations? So one limitation we sort of touched on was the assumption that V2 squared is much higher than V1 squared. I start with this one, and then I'll take you through the inertia term in that expression. To circumvent that problem, or if to sort of not fall into errors from this assumption, if the V1 velocity is at least 1.5 meters per second, it should be put in. So if you're dealing with a situation where a patient, say, has an intra or a subvalvular gradient, and you're calculating or measuring the gradient with continuous wave Doppler through the aortic valve, that gradient 4V squared based on the peak velocity through the valve is not correct if you want to use it to get the pressure gradient. You have to subtract V1 squared from the V2 squared. Now let's talk about the inertial terms. When the blood is in motion, at first, or to set the blood in motion, there is inertia that has to be overcome. At the maximum velocity, the rate of change of velocity with time, if you were to draw a graph relating velocity and time, it will be the peak of that graph, and there the actual slope is zero. It is rather flattish. And with that in place, we can ignore that inertial term. However, at valve opening and closure, there is some energy that will be involved to get that blood in motion, and the ignoring the inertial term may cause problems. Having said that, in normal hearts, this is seldom a factor that we have to deal with. So what are the applications for pressure gradient? PA pressures, gradients across stenotic valves, prosthetic valves, intracavitary gradients, calculating dP dt as a metric of LV systolic function, relying on the MR jet, and likewise dP dt for the right ventricle, relying on the TR jet, then some estimations of LV, EDP, and LAP. Many of you are familiar with the calculation of PA systolic pressure. We say that the pressure gradient between the right ventricle and the right atrium is given by 4V squared. This is TR velocity in meter per second squared. And so the RV systolic pressure is given by 4TR velocity squared, meter per second, plus RAP. If this patient does not have pulmonic stenosis, subvalvular or valvular, or supravalvular, then the RV systolic pressure is the same as the pulmonary artery systolic pressure in the pulmonary circulation. Where does this fall apart? It falls apart if I am not well aligned with the TR velocity and I underestimate it. Sometimes people get the maximum velocity and they don't recognize that they are capturing the peak velocity of the mitral regurg, not the tricuspid regurg, and you end up with very abnormal values and big problems in terms of patient care and report. Where it can also be a problem is when the TR is wide open and there is very little pressure difference between the RV and the RA. Here, the right atrial pressure carries a lot of weight in the calculation, and if we do not get a good assessment of that, we will end up with errors in the PA systolic pressure. By the way, we can enhance the TR jet if we give saline, and we can enhance it with ultrasound enhancing agents if we are using them anyway for better visualization of the LV endocardial border. There are, however, situations where we want to be careful not to take the fully bloomed signal with overshooting. PR is also a valuable signal for us. We can look at the peak velocity. We can look at the end diastolic velocity. The end diastolic velocity, we go to that modified Bernoulli equation, and we say the pressure between PA diastolic and RV EDP is 4, but here it is the end diastolic velocity, not the peak. And we look at that expression and we say we are going to make an approximation that the RAP is very close to the RV end diastolic pressure. Can be valid, may not be valid, say in somebody with severe RV diastolic dysfunction and increased stiffness, but seldom a larger error than that. And so we can estimate PA diastolic pressure as well. Why do I care about PA diastolic pressure? It could be a look at, could be close to LA pressure and would be needed if I want to have a feel also for the pressures in the pulmonary circulation during diastole and to calculate mean pressure. Aortic stenosis, we get continuous wave Doppler and we get it from multiple windows. This is a signal of about 4 meters per second from the suprasternal notch, as you see. This is a very nice signal of a mitral stenosis patient. You can see that the peak velocity is more than 2. And of course, we can get the mean gradient and would not do other measurements aside from the peak velocity, peak gradient, and mean gradient here. Okay. Examples to show you the fidelity of the Doppler measurements of a gradient. These are pressure recordings from the left ventricle and the left atrium with mitral inflow. The patient is in AFib, as you see, and so there is a lot of beat-to-beat variation. If you look at the gradients here, the mean gradient is 10 and correctly captured by Doppler. Shorter RR interval, higher mean gradient, 14 by cath, 14 by echo. And you can go on. Longer RR interval, the gradient is by cath 6, by echo Doppler is 5.6. To get these results, I have to be well aligned with the flow. So we typically get the apical views, we put color, and we try to align with the flow from the atrium through the valve into the ventricle. Dynamic gradients for patients who have, say, LV outflow tract dynamic obstruction, we get that peak velocity and we apply the modified Bernoulli equation. In this case, it's 144. This is the dp/dt concept for quantifying MR. We do not really rely on that. Day to day has been used more in research than really clinical applications. The concept is sort of let me look at the pressure gradient between two time points, one corresponding to 1 meter per second and another corresponding to 3 meters per second. So if you limit it to these two values, then your numerator will always be 32 millimeters mercury. All you need to do is figure out the time, measure the time interval between these 2 points. Rather than using it for the way I presented it to you, you can also use it in a qualitative way. Do I see this ascending limb of the MR going straight line, or do I see sort of bend that tells me that the LV pressure is rising slowly? We can do the same for the TR-JET. These are two examples where the change in velocity is steep and where it is taking a longer time. One slide for estimating the end diastolic pressure. This method is not necessarily the most accurate method. I'm showing it more for concept. So we go for the end diastolic velocity of the AR-JET, and we say that the diastolic blood pressure, in this case was 70, minus the LV end diastolic pressure is given by 4V squared. It follows that the end diastolic pressure is 70 minus 52, 18 millimeters mercury. Why this can result in erroneous calculations, I may not be well aligned. I can end up with a faint signal. Notice that the velocity here ends up being squared. And when you look at a pressure that should have a narrow range of normality, you can see that an error can push it way off the true value. So I'm going to stop here. Thank you. Anybody has questions or wants to make comments, you're welcome. Okay? Yes, sir.
So when we are using continuity equations, at least to like figure out regurgitation fraction, like suppose if you are trying to calculate AI, you say RVOT. So if someone has TR2, so can we just calculate like TR volume, like using continuity equation and just add on to it, or it's more prone to like error and it's not?
So the
first thing, or one of the first comments is how significant the other lesions that are present. If they are sort of in the severity of being mild, coexisting regurgitant lesions of mild severity
or less will not have much of an impact. One approach that I showed you is the aortic flow minus the RVOT flow. Another way to quantify aortic regurgitation is the following, is to say I'm going to get that true stroke volume of the ventricle, the difference between end diastole and end systole, by 2D or by 3D, provided I do not foreshorten the ventricle and I have a reliable volumetric measurement, and then I'm going to measure the flow across the mitral valve. So by going after the regurgitant volume by multiple methods, you can have more confidence in your value. So this is what I would say to sort of briefly answer your question.
Thank you.
There are also other color-based methods to quantify AR that you can use and use them as a check.
So I have a question. So, I was in the past lab to see a doctor do the aortic stenosis with a blue dilation. So, which way is best to use for to monitor the pressure gradients through the AS between Hancock and the Doppler method?
Not familiar with the Hancock you just referred to. The Doppler approach that I just showed you, if you are well aligned, you should get very good results. By the way, in the cath lab, they have their catheters in, so they can see the real change in gradient by pressure measurements rather than sort of wait for us and take the concern of whether we are well aligned or not.
Thank you.
Okay? Thank you all.